Okay, the last topic we're going to talk about in the class is chemical and electrochemical equilibrium. And this differs from what we've been talking about so far, in that so far we've been considering mostly changes in phase. And such changes in phase can involve compositional changes, right? So these can involve compositional changes and also segregation, right? A lot of interesting things can happen during a phase change. But this is different from a chemical reaction, right? Because in a chemical reaction, the identities of the molecules are actually changing, but not changes in the identities of molecules, right? So here we're going to start talking about chemical reactions, but we can use a similar. So in chemical reactions, we can still use a similar formalism to think about the thermodynamics of the reactions. And this will be important for thinking about things like electrochemistry and galvanic cells and these sorts of things. So let's start with just the simplest chemical reaction, right? So let's start with here. Simplest chemical reaction. And the way we're going to express that is just that we have some chemical A that's converting to chemical B and that can convert back. So we have some kind of interconversion process between A and B. So what does this imply? Right? So this implies that we have a mixture of A and B, but because they're interrelated through this chemical formula, but the number of moles of A is not independent from the moles of B, right? In particular, we know that we could write down an expression for our free energy or change of the free energy due to interconversion. So that would be dG would be equal to mu A dNA plus mu B dNB, right? And we would expect that dNA would be equal to minus dNB. Because if we convert a certain number of moles of A to B, we lose a certain number of moles of A and gain the comparable number of moles of B. So it's typical to describe this in terms of an extent of reaction. So it's typical to describe the progress of the reaction in terms of an extent of reaction. And we're going to denote that as dC, and that in this case we can define that with one or the other of these two molar quantities. So in this case we're going to say that's equal to dNB, right? And then once we've defined that, we can rewrite our expression for the change in the free energy to just be equal to mu B minus mu A times dN xc, where xc is this extent of reaction. And then once we've done that, we can define, so we can define the reaction free energy per mole as, we're going to write that as delta Rg, and notice this is, remember this is per mole, and that's going to be the partial derivative of the free energy with respect to the extent of reaction, which has units of mole, at constant pressure and temperature. Okay. So we can see that just by looking at this, in general, delta Rg is going to depend on the current composition. That is, it can change as the reaction goes on. And typically equilibrium will be reached when delta Rg equals 0, right? When we've minimized the free energy by taking the reaction to the point where any change, any further conversion, interconversion, would just increase the free energy. And so we typically say that if delta Rg is less than 0, then we call that the forward reaction, right? We say the forward reaction is spontaneous. So that's known as an exergonic reaction. Or if delta Rg is greater than 0, then the backward reaction is spontaneous, and that's known as an endergonic reaction. Okay. So let's think about this just in terms of one specific case. So let's make a little box here. So let's think about this in terms of gas phase reactions. So if we think just in terms of gas phase reactions where A and B are ideal gases, so that's kind of a very idealized case. So in that case, we'd have delta Rg, right, would be, like we said, mu B minus mu A, right? And so we could write these down in terms of the relations we know between the chemical potentials and the partial pressures. So we could write this as mu B in the reference configuration plus RT natural log of PB, the partial pressure of B over the reference pressure, right, minus mu A theta minus RT natural log of PA over P theta, right? So that gives us an expression for our delta Rg. So what we get is that delta Rg is going to be equal to delta Rg theta, which is just the difference between, so delta Rg theta is by definition going to be mu B theta minus mu A theta. That is the difference of the chemical potentials in the reference at standard molar pressure and standard, right, the difference in the standard molar Gibbs free energies per mole in the reference configuration. And then we're going to have a term here plus RT, natural log of PB over PA, right? So since delta Rg is equal to 0 in equilibrium, right? We know that in equilibrium, delta Rg theta would be equal to minus RT natural log of PB over PA, right? And it's typical to write this as minus RT natural log of K, where K is what we call our equilibrium constant. But is just given by the ratio of the equilibrium partial pressures of B to A. Okay.